This is assignment 11 for Math 465. Let's start with exercise 1, which has multiple parts, and let's see what the scenario is. This is a scenario that arose in assignment 10, where we have an assembly line worker that needs to install a part in a device, and they aren't always successful on their first attempt or even their second, but on each attempt they have a probability of 0.78 of being successful. And we assume that each success is, whether or not on each trial they're successful, is independent of how they did on previous or future attempts. And this worker needs to install 10 such parts in a day. So the first part of the exercise here asks us, what's the probability that it'll take them 12 or more tries to install 10 such parts? So if we look, the thing that we're trying to find the probability of is the variable, which is 12 attempts to install 10 parts. So you can see our variable is the number of trials, and what's fixed is the number of successes that we're looking for. So when we have a fixed number of successes and a variable number of trials, that's a negative binomial situation. And so what we want, we're looking for the probability of 12 or more tries to install the 10 parts. So this is our probability statement. We want to know whether the probability that the number of attempts will be greater than or equal to 12. That will be, in terms of the cumulative distribution, 1 minus the cumulative distribution evaluated at 11, because this is a discrete probability function. And if we think about this for a moment, that seems like that should be all the values from 0 up to 11, but since 10 parts need to be installed, the minimum number of trials is 10 to install them. So actually B star of 11 is really just little b star of 10 and 11, because the probability of installing 10 parts in 9 or fewer trials is 0. So we can just simply take 1 minus the PDF evaluated at those two values, 10 and 11 trials for our 10 successes. And the result is the probability 0.7333. In part B, what we ask for is the probability that during a 5-day work week, it'll take the worker 12 or more tries to install all the parts on exactly 3 of the days. So we're looking for a fixed a fixed number of successes, in a sense, 3, but, well, I'm sorry, our variable would be the number of days that it takes, or the number of days in which this worker takes 12 or more tries to install the parts in a 5-day week. So that looks a little bit like it could be a Poisson process, but we're not looking at the 5-day work week as a continuum. We're looking at each day as a trial, and really the question is, on a particular day, will it take the worker 12 or more tries to install the part? So we're looking at the 5 days as being trials, a fixed number of trials, and we're going to consider a day on which the worker takes 12 or more tries to be a success. So we're looking for 3 successes in 5 trials. So that's a binomial situation then. We have a fixed number of trials, 5, and the variable is the number of successes, the number of days on which the worker takes 12 or more tries to install the parts. So we're just looking for the probability that capital X equals 3. It's just a binomial, 3, 5, and the probability is our probability we found in part A. This is the probability of it taking 12 or more tries for the worker to install the 10 parts. And the result is 0.2805. Now we go to the same sort of situation. We want the probability that during a 5-day week it will take the worker less than 12 tries to install all the parts on 1 or 2 of the days. So this is just like the part we did before, just the very last part, except rather than 3 days, we're looking for 1 or 2 days, and we're looking at the complementary probability. We're looking at the worker taking less than 12 tries. So again, it's binomial. The values of the variable that we're looking for are 1 or 2. We can write the probability statement this way. Probability that The random variable takes the value between 1 and 2 inclusive. Of course, since it's discrete, this really means x equals 1 or x equals 2. And so it's binomial. Again, we want the values of our variable to be 1 and 2. The number of trials is 5. This is the probability. This is 1 minus the probability of it taking 12 or more tries. So this gives us the probability of taking less than 12 tries. And here is our result. Going to number 2, we're back to our spacers that we encountered in assignment 10. And remember, we want the spacers to be a thickness between 0.05 and 0.07 inches. The spacers we get from our supplier are normally distributed with a mean of 0.0608, almost exactly halfway between those two. Standard deviation of 0.0047. So the key here is we want to make note of this fact that the thicknesses are normally distributed, so we'll be using the normal distribution. And we want the probability of a randomly selected spacer having a thickness of 0.055 inches or more. So we just apply the normal distribution. We're looking for the probability that capital X is greater than or equal to 0.055. We can get that from our PDF, our probability density function, by integrating from 0.055 to infinity. In terms of capital N, that's going to be 1 minus capital N of 0.055, because remember, capital N is from negative infinity up to 0.055. So to get the part from infinity, or from 0.055 up to positive infinity, we need 1 minus this value, which is from negative infinity to 0.055, and this is the result. Now this refers us back to the previous assignment, in which we found that the probability of selecting a spacer meeting the desired specifications between 0.05 and 0.07 was 0.9641. So assume that we're installing these spacers, and we check each spacer before installing it, make sure it falls within the right tolerances. And the question is, what's the probability we would select 20 satisfactory spacers before obtaining our first one that doesn't meet the specification? So the thing that could vary would be the number of satisfactory ones before we get a bad one. And we're really looking for, when do we obtain the first bad one? How many trials is it going to take us? So looking at the first bad one as being a success, we're looking for our first success. How many trials does it take? So since the number of trials is a variable, this is a negative binomial distribution. Now we have to be careful, because the negative binomial measures when, on which trial we get what we're after. And what we're after here is actually the first one that doesn't meet the specifications. So the number of trials we're looking for is not really 20, but 21, because that's when we get the first bad one. So that's the number of trials. The number of successes is 1. We're just looking for one that doesn't meet the specifications. So we want the probability that our random variable equals 21. Negative binomial of 21, our number of successes, in other words, number of bad ones, we're looking for just one, the first one. Here's the probability of a bad one, because our probability of getting a good one was 0.9641, so we subtract that from 1 to obtain this value. This shows the formula for the negative binomial, and when we evaluate, we get the value 0.0173. Now we move to a situation where we're working with solar panels that have some sort of small flaw or blemish, and it's known that we end up getting generally 0.037 flaws per square foot. Okay, and so what we're looking for, if we think of a flaw as a success, we're looking at flaws in continuous regions of space, or of areas in this case. So when we're looking at numbers of flaws in a region of space or time that's not cut up discretely, then we're looking at a Poisson distribution. So here the question is, if we have a 3 foot, whoops, oh no, if we have a 3 foot by 10 foot panel, question is, what's the probability that it will have 4 or more flaws? Okay, so our number of flaws is 4 or more. That's our variable, is the number of, we'll call a flaw a success, and we're looking within a region of surface area, so a 3 foot by 10 foot panel. So in this case we're using the Poisson distribution. This is our lambda, 0.037. The T is the area that we're looking at, so we're looking at a 3 foot by 10 foot or a 30 square foot area. And so if we take lambda times T, 30 square feet by 0.037, we get 1.11. So here's our lambda T portion, that's our parameter part. Here's our number of flaws. We're looking for the probability of getting 4 or more flaws, so we would have to sum this. It's a discrete distribution. Sum it from 4 up to infinity, or take 1 minus the cumulative distribution from evaluated at 3, and we get 0.0265. Here we ask how many flaws would we expect a panel to have on average. There's 30 square feet in a panel times 0.037. This exercise is just to illustrate really where this point, or what the lambda T really represents. This lambda T is the expected number of flaws in a 3 foot by 10 foot panel. And so that is 30 times 0.037, or 1.11. Coming down here, now we have a situation, we've got trucks passing through a weigh station. The average rate at which they come through is 23 trucks per hour. And assuming the arrival of trucks is a Poisson process, what's the probability a person working the weigh station would see 175 or fewer trucks pass by during an 8-hour day? So we need to take our 8-hour day, and that would be our T, and our lambda would be 23 trucks per hour. So if we take 23 times 8, that would give us the expected number of trucks in an 8-hour day. And we're wanting to know what's the probability that we would see 175 or fewer under those conditions. So we're looking for the probability that our random variable, the number of trucks, is less than or equal to 175. That would be the sum from 0 to 175. We could have no trucks at all, of the PDF. And lambda T again is 184. That's from 8 hours a day times 23 trucks. And this is equivalent to the cumulative distribution evaluated at 175, gives us the value of 0.2679. And that concludes assignment 11.